Hello everyone, welcome back to the another session in design and analysis of algorithms. The topic name is proving graph problems. This topic you will find in 5th unit as topic number 5. The previous video is about NP-hard graph problems and this is what proving graph problems. So I am just giving the index that was into first part and this was into second part. Whoever is watching this video or advised to watch the before video so that you can understand this video completely. Okay, now let's get started. That CDP, click decision problem, is a graph problem and also we have to prove that it is a NP-hard problem. If a decision problem is NP-hard, then decision problem also NP-hard. Both are NP-hard. Proving graph problem as a NP-hard. Now we'll be going to prove CDP is NP-hard. Now how can I prove that? Say that problem is L2. That means P is equal to L2. We have to prove problem L2 as NP-hard. To prove, we have to select a problem which is already NP-hard. That's what we were seen in the first slide. If you wanted to prove CDP is a NP-hard problem, you should take the problem which is already NP-hard. Now let's name it is L1. So now you have to reduce this L1 to L2. That is, we'll take some instance of I1, we'll take some instance of I2. Now we will be solving this L1 with this instance in polynomial time. If it is also possible to solve for this instance L2 polynomial time, then we say that satisfiability known NP-hard. We take this to prove CDP. We take this to prove click decision problem is NP-hard. Now what we will be going to do is, I wanted to prove CDP as NP-hard. So for this, what NP-hard graph strategy we considered in the first slide? Whatsoever problem you wanted to prove NP-hard, first of all take one NP-hard problem which you know. I know about satisfiability. Satisfiability problem is NP-hard problem because exponential time complexity 2 power n. We made already a video on satisfiability, why it takes exponential time and what is the relation of NP-hard, that you can watch that video before you come to this video. Now my aim is what? I wanted to prove this click decision problem as NP-hard. So according to the strategy what we were discussed in the first slide of this video, you have to consider one known problem. That known problem is satisfiability. Now L2 is CDP, L1 is satisfiability. So now what we will be doing is, we'll reduce this satisfiability to CDP. Now let's see how we will be going to do. Now consider satisfiability formula, which is CNF, consecutive normal form, that with the arbitrary values x2, x1, x2, x3. Now that formula is what? x1 r x2 conjunction x1 r x2 x1 r x3. Now there are three classes what I have taken, C1, C2, C3. On base of what the classes will be, that the classes formula is what? Ci consecutive I is equal to 1 to k, consecutive normal formula is equal to. Now the k value is what? K value is 3. So I have taken k value is 3 classes. Now so take this as a vertex. Take these values as a vertex. Now I am taking as a vertex. So I am just taking x1 and x2 as the vertex. x1 and x2. Figure out x1 and x2 from the first class. x1 is the first class. x2 is also from the first class. I am just writing the arbitrary value, arbitrary number or x value and the from which class I am taking, C1, C2, C3. So I am just denoting it. So this vertex is what? X1 comma 1. X1 is this number, 1 is represents class number, and this is what? X2 comma 1. Now we'll take even this. These are what? X bar or negation. Negation x1 dash. So this one x1 dash comma 2. Correct? Now x2. Let's take that. This is what the value? X2 bar comma second set, second class. And we'll take even for this. And this is what? X3. This is what? X1 comma 3. And this is what? X3 comma 3. Fine. Now what I'm going to do is, can I make a real edge in between x1 to x dash? Yes, no. The reason is, if I take x1 value 1 true, x dash means what? Negation of x is false. If x is true, x1 is false. That means I cannot form an edge in between these two vertices. Correct? Now, how I can make this pair? That I have a formula which is z is equal to G graph is equal to vertices a comma I, where a is belongs to ci. We should not draw a edge from in the same class. That's it. 1 point. There are properties what you have to follow. The first property, we'll write 1. The first property to form a edge is, you should not draw any edge from the same class. No, not to draw any edge from same class. You cannot do it. And I can connect vertex of one class to the another class. The second point is, you cannot draw an edge to the x1 to x1 dash, because those two are opposite. And forming of these edges, you have a formula that E is equal to a comma I and b comma j. I naught is equal to j and b is not equal to a dash. That's it. Now with this we will be going to join again. The first clause is what? X1 and X2. Second clause is what? X2, X1 bar and X2 bar. Third class is what? X1 and X3. Now let's, this is what? X1 comma 1. And this is what? X1 comma 1. This is what? X2, this is what? X1 bar comma 2. And this is what? X2 bar comma 2. This is what? X1 comma 3. This is what? X3 comma 3. According to this property, you have to connect the edges. Now I am connecting the edges in between one class to the other class. 1 to 2 there can be. This is one class and this is second class. Now I can connect a edge from this. And it is from 1 to 3. I can connect an edge. And this is also from 1 to 3. I can have an edge. And here to here also I can have an edge. From 2 to 3 also I can have an edge. And it is 1 and it is 3. So I can also have an edge. So this is 2 and this is 3. I can also have an edge. Correct? So these are the what possible edges of this particular vertex. Now the point is what? K is equal to 3, because we were taken 3 classes. We were if this is solved, then you can find the graph which is connected. That's what, right? What is CDP? We wanted to reduce this CDP problem. We wanted to find the CDP is what NP had. So I am taking satisfiability, which I know, and that I am converting into CDP. What is CDP? Having a subgraph with the complete graph. So find out any subgraph over here. So the subgraph is this with the completed graph. Now let's see. Now satisfiability is what? CDP. I have reduced satisfiability problem to click decision problem. Now Now you can say that CDP belongs to NP hard, because you proven whatsoever is NP hard, example satisfiability, and you reduced that to CDP. Hence, now you can also say this one, that is what? Now F is equal to, what is your consecutive formula? X1 or X2, X1, X2, X1, X3. Now what are the values of this? X1 value is what? 0. X1 bar will be 1. Correct? Now, so X1 is again 0. What is X2 value? 1. And X2 value is 0. And X3 is 1. Now, 0 or 1 is 1. Now, 1 or 0? 1. 0 or 1? 1. So, finally, this is what? 1. True. It is true. What it is true? That satisfiability problem is NP hard, and which is reduced to click decision problem. So it is true that click decision problem belongs to NP hard. And please remember this point very carefully, that the point is what? NP hard all the NP hard decision problems we deal with here are NP complete. The construction of polynomial time non-deterministic algorithms for these problems are left for an exercise for an research. But all NP hard decision problems are NP complete. That means we proven NP complete problem to be NP complete problem with the example which we know with the satisfiability constraint. This is what about proving graph problem and click decision problem. Thank you all.